now. And nice catch, Emma. So right here, yeah, I wrote the problem, and then I went down here to write it again, and I didn't do a good job, because that should be a plus, and that is going to change some stuff, right? So what does that look like? That looks like a plus, which makes this a plus, which makes this a plus, which instead of dividing x minus 4, it divides x plus 4. All right. I am happy to tell you I am not perfect and make mistakes. I do my best to avoid them, but they still happen sometimes. So never feel like you are, I don't want you to feel like you can't say something if you think I did it wrong, because I remember sitting in a CS class and, no microphone. I don't, other than a muted, other than the volume is low, but you can hear all the beeps coming up. Can't think of anything. X plus 4, let me finish this off, get it right. The plus 4 is divide, the 4x is divide. Left with x minus 4. Yeah, anything specific? Speakers. That's all right. Okay, so great catch, Emma. I love it. I left you with, good. All right. So I left you with 2 problems. I ask you to simplify these. These are both rational expressions. Again, expressions, and this is me trying to get the language correct. Expressions do not contain equal signs. Equations contain equal sign. So when I say simplify this expression, this is what I'm talking about. It does not have an other side, or how we say other side of the equation. This doesn't have an other side. Since it's an expression, it limits what we can do. So I can't multiply, I can't find a clever way to add 0 to both sides because there's not 2 sides. So I have to be careful with that. This one breaks down. Let's see. So remember, the negative powers mean it's whenever you see a small child doing something they're not supposed to do, they get that look on their face, like I'm not supposed to be here, I'm probably going to get in trouble. That's all that negative means. I'm in the numerator, I'm supposed to be in the denominator. So it goes like this. So d to the negative 2 is 1 over d squared. C to the negative 2 is 1 over c squared, and then so on and so forth. Now, to deal with this, there are 2 ways to tackle it. We can either multiply the top by the common denominator on the top and bottom, and then find the common denominator down here and do the same thing, or I could find the common denominator for all 4, and this is something we didn't do last time. What is the common denominator? For all 4 fractions. Okay, so instead of dealing with the numerator separately, we can do this all in one step. Okay, well, I have a d squared, so least common denominator is going to have a c squared and a d squared. That covers these as well, right? There's no new terms. This is a c, this is a d. Exactly. So since that's the LCD, I am just going to multiply the top and bottom by the LCD. Okay, it's going to prevent the confusion, hopefully, of trying to make the numerator and denominator do different things. And what happens when I do this? When I distribute this, I'm gonna do this in I'm gonna do this out one time, and then we will reduce it, just so you see what's going on. C squared d squared over d squared minus c squared d squared over c squared over c squared d squared over d minus c squared d squared over c. Now, we're clearing the fractions. So if I did this right, the numerator and denominator, the fractions will go away. I won't have a complex fraction anymore. D squareds divide away, c squareds divide away. One of the d factors divides and one of the c factors divide. So what's left? Numerator, I have c squared minus d squared over c squared d minus c d squared. All right. What's next? Ideas? C squared and d squared cancel out. I wish they did, but they don't quite do that yet, because the numerator, both of the terms in the numerator would have to have a c and a d in it, or a c squared and a d squared in it, but they don't. But I can continue factoring. I can continue working. Okay. Well, this is the difference of perfect squares, right? C squared minus d squared. That factors into c plus d, c minus d. The denominator, both terms have a c in it and both terms have a d in it. So I can factor out cd, and that's going to leave me with what? Well, that's going to take away one c and all of the d's. And this is going to take away one c and one d. So I'm left with c minus d and c minus d. These divide. And my final answer is c plus d over cd. So compare that to the way we did this before, where we had I found a common denominator for the numerator, I found a common denominator for the denominator. I got common denominators, I added or subtracted, and then multiplied by the reciprocal. This one goes a lot quicker. Okay. And so let's move this down to the bottom. And let's get this last one out of the way. So I have, and if this is too small, tell me. Pop that out so you can see. I have another complex fraction. That 2 has 1 plus h in the denominator, and then all of that is minus 2, then the whole thing is divided by h. So to do the same, I found the common denominator for all the fractions. So I went through, I looked at them. So the common denominator, the denominators are c, d, c squared, and d squared. C doesn't change, d doesn't do anything, but c squared is c times c, d squared is d times d. So everything that occurs in multiples, we count once. So that means the c's, that's 1. The d's occur, that's 2. And then everything that doesn't repeat anywhere gets counted once, times that c times that d. So now I have c squared, d squared. Okay. All right. So I already mentioned up here the LCD for the numerator of the next problem. So, well, I said it's what? Well, this is, and again, 1 plus h minus 2. I can write, anytime I have an integer, I can rewrite it as itself over 1, because dividing by 1 does nothing. And so I have a numerator that has 2 fractions in it. What's the LCD here? Well, just like the piece before. This has a denominator of 1. This has a denominator of 1 plus h. So my LCD is 1 times 1 plus h, because this doesn't have a factor of 1. I know it's got the 1 plus, but that's not just 1 sitting by itself. So I've got 1 times 1 plus h, which is 1 plus h. So I need to make this fraction I can either see it as make this fraction look like 1 plus h, make it have the same denominator, or I can do what I did before and clear the fractions, right? And to clear the fractions, I just multiply top and bottom by the LCD. I'm allowed to do it because the denominator does the same thing. It's got a 1 down there as well. So we know that 1 plus h is the LCD. So multiply this through, and I'm going to get 2 minus 2 quantity 1 plus h over h times 1 plus h. Now I did 2 steps here. I multiplied every numerator by 1 plus h. The 1 plus h is divided for the first one. That's where this 2 comes from. The 1 plus h does not divide here. It just stays on top. So that's where I get the 2 times 1 plus h. And in the denominator, h times 1 plus h is h times 1 plus h. Do not multiply through until you've completely factored everything, because you may have a common factor that you'll miss if you're not careful here. So numerator has 2 2's in it, or each term has a 2 in it. So I'm going to factor that out. And then here's the toughest part. When I do that, take this 2 away, divide by 2 is 1, minus 2 divided by 2 is 1. And then in the denominator, got h times 1 plus h. Well, I can do some subtraction here, right? Now that that 2 is gone, I can just distribute that subtraction to the 1 plus h. And now I'm looking at 2 times 1 minus 1 minus h over h times 1 plus h. What is 1 minus 1? It is 0. I'll answer that. And then, so that's 2 times negative h for h times 1 plus h. And what have I got? Have anything in common? Yeah, I can divide these h's. If I divide this h by h, this is a negative h. So that's going to leave a negative 1 here. I divide that by h, it just leaves a 1. And what do I have? I have negative 2 over 1 plus h. All right. So, lots of fun ways to tackle the problems. All right. Specific questions here. Again, I know we're recording, so you can always come back and play this. And now that I have that Loom app, I can make videos really quick. I can actually make them on my phone and submit them, so you can ask me a question and I can just respond to you verbally if I'm away. The videos, if I will send them as they pop up. The regular lecture videos are in Blackboard under recordings. I'm going to post those on Loom as well. And let me play with Loom a little bit more, and let me see if I can dedicate a playlist or a group of videos for just the class. Okay. So next I got 2 examples. What I'm going to do, again, we are just burning time right now. So I'm going to tell you that the solution to this is 2x. And the solution to this one works, this skill practice 8, it works exactly like the problem we just did. The solution to this is -1 over 1 plus h. Okay, so I'm going to leave those for you to do, and then I'm going to make these videos to, remember I said do the skill problems that are in the notes. So now that we've run across them, I'll make those videos today or tomorrow and post them. All right, so you should be able to do these, get in there, tackle them. These are just like the problems that we just did on the last page, so you got good examples. Okay, last step in R4 is simplifying radical expressions. All right, so in order for a radical expression to be simplified, again, expression meaning that it's just one side, it's not done on an equation, it's just one side. It's a radical expression. That means that x is in there and it is trapped under a root. It doesn't have to be a square root, just any root. So I cannot have a fraction in the radicand, that's what's under the root, and I cannot have a radical in the denominator. You've heard of rationalizing the denominator? That's what this is. Now, why do we do it? Why do we have to rationalize the denominator? The reason is, 1, everybody comes up with the same answer. So for example, if I tell you if I said the answer is 1 over the square root of 2, that would be, if that's the answer to some question I give you. If I multiply this by the square root of 2 over to the square root of 2, I now have the square root of 2 over 2. These are equal because all I did is multiply by 1, right? Because square root of 2 over square root of 2 is 1. So I just found a clever way to multiply by 1, and this is also correct. So rationalizing the denominator lets everyone know when to stop, because some people will go here, some people will take a step further, some people might try to do more. We want you to know you can stop as soon as the denominator doesn't have any radicals in it. The other reason that we do it is it's a carryover from before computers. Dividing by, anytime, let me back that up. Anytime you have the root of a prime number in the denominator, you're dividing by an irrational number. Irrational meaning the decimal goes on forever and ever. Dividing by an irrational is incredibly difficult, especially without computers. Over here, my irrational is in the numerator. I'm dividing by an integer. That I can do. Remember, before computers, people sat down and they had to go to their tables, and they had somewhere in the table, it would say the square root of 2 is approximately, and then it would round it out to decimal places. So that's what you're seeing. You're seeing a remnant of, prior to computers, you're seeing a remnant of the slide rule, but we still do it today. We do it because it makes the answer always a nice number. They're also going to run into some things later on in 172 when you get to the unit circle, where having an integer in the denominator makes dividing up the unit circle a whole lot easier. So how do we do this? What do we do to get rid of radicals in the denominator? Well, the answer is almost always, and I say almost always because there's always an exception, I'm going to multiply to get rid of this root. I'm going to multiply the denominator by its reciprocal, all right? And the reciprocal is just take the exact rational expression you see and swap out the middle operation. So in here, this is positive, or this is plus. So the conjugate of 5 plus 2 root x is 5 minus 2 root x. You don't have to be radical to have a conjugate. Conjugate just means change the operation in the middle. And the reason that we like it, the only reason you would have it is because when I multiply this, so that's the conjugate, I'm going to multiply by 5 minus 2 root x and 5 minus 2 root x. What happens? Minus 2 root x over, and let me make this a little easier to follow. Well, you probably can deduce that if my goal is to get rid of the radical in the denominator, I'm probably doing something that's going to help me with that process. And that's exactly right. So I got 3 times 5 minus 2 root x over, now we FOIL, right? First, outer, inner, last. And they are 5 times 5 is 25. Outer, 5 times negative 2 root x is negative 10 root x. 2 root x times 5 is positive 10 root x. And then 2 root x times negative 2 root x is negative 4 root x squared. Look at these middle terms. They go away. Negative 10x, negative 10 root x plus 10 root x is 0. Okay. So still dealing with the same problem, 2 root x. And remember, all the work I'm doing right now is in the denominator. And then in the denominator, I have 25. These subtract away to 0. And then I have minus 4. What is the square root of x squared? I'm doing inverse operations, right? I'm taking a square root and then I'm squaring it. Anytime that happens, I end up with exactly what's under the root, right? The square root of x squared is x. Okay. And can I do any more than that? I could distribute the 3 if I wanted to, but there's no need. So that's it. 15 minus 6 root x over 25 minus 4x. And again, remember, the goal here was to rationalize the denominator. The answer does not have to be pretty. In fact, it's not. And that is absolutely fine. So don't let, whether we realize it or not, we kind of let how ugly an answer is determine if we think it's right or not. Don't let that fool you in here. Rationalizing the denominator can make some nasty things appear. All right. So how about this next problem? Okay. This is one of those, if you know, you know. But if you don't, it's okay. I'm just making myself some more space here. Okay, because there's 2 ways to tackle this one. We're dealing with the rationalizing the denominator, so let's stick with the plan. So the denominator has square root of x minus 2. I'm going to multiply by the conjugate to get that root out of there. Multiply by conjugate. I am practicing my handwriting. It doesn't look like it, but I am. All right, anybody want to tell me what the conjugate of the square root of x minus 2 is probably? You know it's going to have a square root. You know it's going to have 2. It's the only thing that changes. Yep. Plus sign, exactly. So whenever I get the conjugate, I just swap out my operation. In the problem, I'm doing minus, so the conjugate must have a plus. And the whole purpose of the conjugate is to make the root go away. Anytime I multiply some radical by its conjugate, what I'm going to end up with is a real number. Okay, or I'm going to end up with a rational number. In the numerator, let's get out of the red here. And I've got x minus 4 times square root of x plus 2, all divided by square root of x times the square root of x is x. Square root of x times 2 is 2 root x. Negative 2 times x is negative 2x, negative 2 root x. 2 root x minus 2 root x is 0. So in the denominator, the middle terms go away. Negative 2 times 2 is 4. I got the root out of the denominator, didn't I? Anything else I can do? Well, actually, there is. Look at that. There's a root, x minus 4 and x minus 4 sitting there. They're both factors. So what happens? Well, they go away, and I'm just left with square root of x plus 2. That was easy, right? It's like my daughter at night, if we pick a short book when it's time to go to bed, she's like, that was quick. That one's not too bad at all. Okay, questions? No? All right, let's tackle the monster problem down here. Yeah, I don't think so. I am partial to it because I enjoy math, but I think you're right. It doesn't seem, it's not nearly as some of the stuff you've already seen us do. Now this one, now this looks nasty. This looks so nasty when you start. You're just like, oh, great. What if the denominator has no second term? When I multiply by the conjugate, I'm always going to get the square of the first term and the square of the, or I'm going to get the, I'm going to get the square of the first term and the square of the second term. And it's always going to be minus in there too, that result of that multiplication. If it was just x in the denominator, then you cannot divide it. It would just be quantity x minus 4 times quantity root x plus 2, closed quantity, all divided by x. And that's all you can do with it. Okay. All right, so let's take on this beast. Your printout may not be as nice. I've figured out how to import equations, so I'm really working on improving the notes as well. But we have x to the 2n plus 1 minus x to the 2n times y, all divided by x to the n plus 3 minus x to the n times y cubed. Do I have any common factors? Yes. Yes, I do. What are they? Well, in the numerator, we both agree, forget about the variables for a second, everyone agrees that the numerator has x in both of its terms, right? X to the 2n minus 1 is one term, x to the 2n times y is the other term. Remember, terms are separated by pluses and minuses. How many x's are up here? How many times am I multiplying by x? Well, this is 2n plus 1 times, and this is 2n times. When I have the same base and I multiply, I add the powers. So I can rewrite this first term as x to the 2n times x to the first, which I don't have to write the 1, but it's there. Why is that helpful? Okay, well, hopefully it lets you in on the secret that the first term and the second term both have a factor of x to the 2n. How about the denominator? Once again, they both have, they both have an x in it, right? This one has x to the n plus 3, this one has x to the n. Well, using that same logic, I can rewrite x to the n plus 3 as x to the n times x cubed. And now here comes the factoring. It's blatant now. The numerator, both terms share an x to the 2n. So what's left over after I do that? Well, this x is left. This entire factor goes. So all I have is y, and the operator just comes from the problem. In the denominator, I have x to the n's in both. And what's left here? Well, x cubed. That x to the n is completely gone. It divided away. Minus y cubed. Everybody okay with that? All right. Now, both of my factors that I pulled out are x's. So I got the same base. They're to different powers. When I divide the same base, when I multiply the same base, I add the powers. When I divide with the base, or with the same base, I subtract 2n minus n, which equals what? 2n minus n is 1n. So the only thing left, I can divide the top and bottom by x to the n, and now I'm looking at x to the n times x minus y over that x to the n divided away by x cubed minus y cubed. Now, I'm going to try to start my notation here so you can follow me. I never like drawing all the way across the page, so I just kind of put an arrow over here to indicate that I'm continuing. The denominator is the difference of cubes. All right, so let me just write this out again down here so you can see, so I don't do something important in the middle. Okay, the denominator is the difference of cubes. The rule says that if I have a cubed minus b cubed, that this is equal to a minus b times, where'd my problem go? A minus b times a squared plus ab plus b squared. This is the thing that I got wrong last time. So the denominator here is, it's not a and b, but it's x and y. Everything matches up. So that means that denominator will break down into what? Well, the denominator is now, let's make it blue now. That's x minus y times x squared plus xy plus y squared. Does that help? Yeah. Well, I mean, help is a tough thing to say here. There's x minus y's, there's factors of x minus y in the numerator and denominator, so I get to divide those away. So what do I have left? I have x to the n divided by this trinomial, x squared plus xy plus y squared. And if you're wondering, one day I'm going to finally pick if I write my 2's with a loop or if I just write them flat. That day just hasn't happened yet. So maybe it's something that happens in your 40s. I just haven't quite gotten there. Okay. That's one of the more devious problems out of R4. Any questions here? Emma, I just saw what you said. I'm going to glance up and then I'm going to come right back. If there was no minus 2. Let's see here, would x to the n divided by x squared minus y squared? No, it would not. And the reason is that this this does not break down the way that you're thinking it does. Because remember, so what you said is if I had the denominator is what she's saying is, does this denominator become this? And the answer is no, because the middle term is there. The middle term doesn't work the way you want it to, because to break this down, I need two things that multiply to y squared, two things multiply to x squared, and then when I add them together, they have to be xy. So if you think this does this, if you think this is x plus y times x plus y, it's actually x squared plus 2xy plus y squared. Because one xy, there's the other xy. So we put them together, and that 2 is there. That's why that I said this. This is the mistake I made last time. That the result of that cube being broken down, this typically does not factor. All right. It would if there was a 2 in front, but it doesn't. But there's not, so we would just leave it exactly like this. And this is a place, so people talk about using Mathway or using online stuff, and I want you to have those tools and to use them, but I want you to use them to check your work. I'm absolutely fine with you getting done with this problem, doing the best you can, and then checking this on Mathway. That is not a concern. I just don't want you to get used to looking at Mathway for the answers, because obviously you can't do that on the test. So this is a great problem where this one has a lot of things, there's a lot of moving parts, a lot of stuff that can go wrong here. So absolutely check your work there. I try to use examples from the book where the answer is published in the book, because I want you to not only work hard and do everything, but I want you to know you have the right answer so you can see what you did right or see what you did wrong. All right, well, that's R4. Questions? All right, so R4 homework will be due next Tuesday, and R5 will not, but I'm going to leave it up so that way you have access to it. All right. Anything else? I think we're good. All right, and let's tackle R5. So R5 has two parts. The first part is quadratic and rational equations. This is going to feel like a repeat because you've done this before, but follow along with me anyway. So we got a quadratic equation. First off, I'm going to show you some notation. You're going to see it down here. I've got first line of this definition says let A, B, and C represent real numbers. I'm going to shorten that using mathematical notation. A, B, and C are elements of the real numbers. That is the same thing as what is written here. So let A, B, and C be real numbers. Okay? You'll see down here in the zero product, I use that notation. I want you to get used to it. So those are real numbers. That just means they're not complex. Okay? Where A is not zero. Well, if A was zero, look at this quadratic equation. If that's zero, that whole term goes away, and now I have a linear equation. So that's why we have to state for the record that A cannot be zero. So if I have real numbers A, B, and C, a quadratic equation in the variable x is an equation of the form ax squared plus bx plus c equals 0. All right. What we're going to do in this section is we're going to learn to use the zero product property, the square root method, the quadratic equation, and completing the square to solve quadratic equations. All right. So let's break down what does this mean? Okay, or what are we doing here? Well, I need to introduce the property on the left first. It's called the zero product property. You'll hear me say zero product principle as well because I've heard it called both. And it's a really basic concept. It says let m and n be real numbers. If m times n is equal to 0, then m equals 0 or n equals 0. Also, both could be 0. but this is what we want out of it. If two things multiply to 0, one of them has to be 0. This is the only number that has this feature, right? If two things multiply to give you 2, you're not guaranteed one of them is anything, right? Because I can get 1 times 2. I can get 4 times 1/2. I can get 8 times 1/3. There's no guarantee what one of those two numbers is. This only works for 0. And the reason it works for 0 is because anything times 0 is 0. And if you multiply two numbers that are non-zero, you will never get 0 as the product. So it's a special feature of 0. So how am I going to use this to my advantage? Well, I'm going to work my way to a problem where I have two things multiplying to give me 0, and then use it. So let's solve this equation down below it. 3n times quantity n plus 2 is equal to 4 minus 5n. Okay, so I'm going to distribute on the left. 3n times n is 3n squared. 3n times 2 is 6n. The right-hand side has nothing, no math to do. This is a quadratic. No common terms on the left to add together, no common terms on the right to add together. So I don't need to combine like terms yet. I combine like terms with these two, can't combine like terms with the two on the right. So now it's a quadratic equation. I need one side to be 0. So when I'm dealing with quadratic equation, I'm going to get everything on one side. So that is going to result, that's going to mean I'm going to move everything to the left just because that's habit. So I need to subtract 4 from both sides, and I need to add 5n to both sides. So what does that give me? 3n squared is not impacted. 6n plus 5n is 11n. And then there is no constant term over here, so just 0 minus 4 is -4. All right. So I have 3n squared plus 11n minus 4 is equal to 0, and I'm asked to solve it. Well, this factors. You can do this with the bottoms up method. You can do this in a whole bunch of ways, but this factors into 3n and n. Leading coefficient is prime, so I can get these with ease. It's got to be 3n and n. The last two multiply to 4, and not just any 4, a -4. So that means these two numbers are either 2 and 2 or 1 and 4. And my operation in the binomials is addition and subtraction. So which case do you think it is? Well, if this is 2 times 2, I need to get two things that add to positive 11. And one of them has to be negative, one has to be positive. So if I put a 2 here and a 2 here, I'm never going to get to 11. So it's probably 4 and 1. So I need the 4 over here, so that 4 times 3 is going to give me 12, and then I'm going to take away 1, that's going to leave me 11. So that's a plus and that's a minus. This is the place I want to get to, because now by the 0 product property, two factors have multiplied to give me 0, which means that the first is 0 or the second is 0. And now it's linear equations, right? So get n by itself, add 1 to both sides. 3n is equal to 1. Get n by itself, divide by 3, divide by 3. N is 1/3. Or subtract 4, subtract 4. N is -40. So my solution set contains two answers, -4 and +1/3. Okay, I'm doing the notation and being pretty specific here about how I write the solutions because in the book, the answers in the back follow this form. They give you a they give you a set with the solutions in it. They don't just say n equals 1/3 and n equals -4. All right. So that's the zero product principle. It's probably the most common one that you use. Factor a quadratic so that it becomes two binomials or just any two factors that are multiplied by each other. Get the other side to be 0, and then I have two things that multiply to 0, so one of them has to be 0. All right. So that is zero product principle. That's the zero product principle. The other, or one of the other steps, is the square root method. Okay, so get the equation in the form x squared, and x is just the variable here, equals k, where k is a real number. Take the square root of both sides. Well, I'm almost done there, right? I've already got it in the right form. Take the square root of both sides. But here's the piece you have to remember. When I take the square root of p squared, that's just p. When I take the square root of 18, because 18 is a real number, I have to consider positive and negative solutions. Okay, so think about that for a second. Just come over here to the side and think for a second. The square root of 9, that's not just 3, is it? 3 times 3 is 9, but -3 times -3 is also 9. So if I take the square root of a real number, I have to consider both the positive and the negative answers. And that's what that second line there. Remember, the solutions will be positive and negative k. So what have I got? I now have my variable p is equal to positive and negative square root of 18. And we're going to refresh you on breaking up your roots. 18. Can this break down into, does it have any factors that are perfect squares? So perfect squares, we don't count 1 for this one, but 4, 9, 16, 25, all the way up. This has a 9 in it, right? That's 2 times 9. Well, the properties of squares say that if I have two things under the root multiplied by each other, I can rewrite them as products of the roots of each. Square root of 9 is 3. And whenever you're dealing with roots or with radical numbers, always bring whole numbers or bring integers out front. Don't put them back here, because it's really easy to think that that line carries over and that 3 is still under the root. So the square root of 9 is 3. I brought it out front. There are the solutions. So what does my solution set look like? It contains both of those numbers. I've got 3 times the square root of 2 and -3 times the square root of 2. Thoughts? Okay, still feeling pretty, feels like something you've seen before. That's what we want. How about this next one? How about the next problem? I got 3y plus 4 quantity squared equals 16. This doesn't look like the problem before, but it is just like the problem before. I already have something squared is equal to a real number. So I'm going to do the same first step that I did up here. I want the y to get out. The y is currently in the parentheses and being squared. I cannot do anything until I get this y out of the parentheses. So I need to get it out. How do I get rid of a square? Take square root. If I do it on the left, I have to do it on the right. 16 is a real number, so I got to do positive and negative. The square root of a square is just the radicand, which is what's under the radical. Square root of 16 is 4, and then I have a plus minus over here. Now, to write your answer, this is this is kind of your own personal feelings or your own personal touch. At this point, you want to solve for y, you're going to subtract 4 and then divide by 3. Subtracting 4 and dividing by 3 while you have a number that has a sign with it can be confusing. So what I have here is essentially 2 answers. So I would go ahead and break this up into 3y plus 4 equals 4, and 3y plus 4 equals negative 4. Is everybody cool with that? Everybody good with what I just did? This has 2 solutions. One is the case where I have 4 on the right. One is the case where I have negative 4 on the right. All right. So get y by itself. Subtract 4 from both sides. And then get y completely by itself. 3y is currently equal to 0. I need the 3 to go away. And what I do, I divide by 3. 0 divided by 3 is 0. Okay. And my other solution. Okay, if you're trying to knock that rust off still, solving that linear equation, I want to get y by itself. So that means everything that has a y to one side, everything without to the other. 4 minus 4 is 0. Negative 4 minus 4 more is negative 8. And then I've got everything with the y is on the left, everything without is on the right. Now I just need y to be completely by itself. Divide both sides by whatever the coefficient of y is. In this case, it's 3. I have y is equal to negative 8/3. So my solution set contains 0 and negative 8/3. Whoa, that was just an unmitigated disaster of a right. That's not much better, but and there they are. They are my solutions. Okay, so that's how to use factoring and the zero product principle, and how to use the square root principle. Most of the time we don't actually write out the zero product principle. We just call this factoring, but you're doing 2 steps there. You're factoring it so that you get 2 things multiplied together and give you 0, then use zero product rule to solve the problem. So factoring and zero product are kind of going hand in hand. The square root is when you can get your variable or some algebraic expression squared is equal to a real number, and then go about your ways of taking the square root of both sides or whatever root you need. The other way to do this is the sledgehammer. Okay, here is the sledgehammer. It's the quadratic formula. Why am I calling it a sledgehammer? Because when you have a hammer, and that's the only tool you have, everything looks like a nail. This will always, 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 always give you the right answer. There are some cases where this is the only way to find the factors of a trinomial, or to find of a quadratic equation. And it comes down to the opposite of b plus or minus the square root of b squared minus 4ac, all divided by 2a. For years, when I wrote this out, I didn't pay attention to that x equals on the left-hand side. So this is saying x is equal to the answer, whatever I get after I do this work are going to be the values of x that make this equation true. The values of x that make this equation true are called zeros, because when I plug them in, I know that I'm going to get 0. So in order to use the quadratic formula, the first step is you have to be in this form. You have to be in it's called the general form for the quadratic equation, or for quadratic equations. Ax squared plus bx plus c equals 0. Everything is on one side, everything without is on the other. This is the opposite process, or if you're using quadratic formula, This is not how we solve linear equations. We just did some linear equations where I get everything with the variable on one side, everything without on the other, and then go. Not here. So let's tackle it. Let's come over here to the top right and solve x times quantity, x minus 6, closed quantity is equal to 3. This feels like it's easy, right? And this is where that zero product principle can get you in trouble if you're not careful, because it looks like two things multiply to give me 3. One of them's 3. That's not guaranteed. That only works when I have a 0 over here. So let's distribute x squared minus x is equal to 3. So I've got x squared minus 6x. I'm getting everything on one side. So I'm going to subtract 3 from both sides. Everybody good? That looks disturbingly like an equal sign. Fix that. All right, so this does not factor because there are not two numbers that multiply to -3 and add to -6. At least there's not any integers that do that. I can't make this a square root issue, and this is in the part of the notes where I say use the quadratic formula, so we're going to use the quadratic formula. So a is the coefficient of x squared, that is 1. B is the coefficient of x, the sign goes with it, that is -6. And c is the coefficient, is the constant term, which is -3. Why did the negatives come with us? Take a look at that general form again. What's the operation between each term? It's always plus, right? So if that's always supposed to be plus, this needs to be written as plus -6x plus -3. So that's why the negatives come with the a, b, and c if they exist. Okay, so let's plug in. So x is equal to the opposite of b, plus or minus the square root of b squared minus 4ac, all divided by 2a. And what do I have? B is -6. So that's -6 plus or minus -6 squared minus 4 times 1 times -3, all divided by 2 times 1. Everybody okay with that process? No mistakes found? Everybody looks like I'm doing my math right? All right, let's keep going. -6 is 6, plus or minus the square root of whatever you get here. This is b squared. Whatever the number is for b, positive or negative, the square is always going to result in a positive number, right? -6 squared is 36, positive 6 squared is 36. So this first term under the radical is always going to be positive. And now I have minus 4 times 1 times -3 is minus -12, all divided by 2. I can obviously clean that up some more. Minus negative becomes plus. And then can I go further? Yeah. Square root of 48. Any perfect squares in there? Absolutely. If you don't see any perfect squares, or if you don't think of any, try taking 2 out and then take it out again. And then take it out again and again if you can. Turns out 48 breaks down into 16 times 3. The square root of 16 is 4. And then all 3 terms that are left have a 2 in it, right? That 6 is divisible by 2, this 4 is divisible by 2, and this 2 is obviously divisible by 2. So I'm going to factor out the 2 in the numerator. That's going to leave me 3 plus or minus 2 root 3 divided by 2. Why did that help? Because I got rid of some more 2's. So what do I have now? I have x is equal to 3 plus or minus 2 root 3. So my solutions are 3 plus 2 root 3, 3 minus 2 root 3. Any questions? Oh, you can't see the bottom of the screen. All the way to the right. Questions on this one? All right. Well, let's take the last few minutes of class. Let's finish this page. And then we'll see what to do next. All right, so up here on the top left, everyone's worst nightmare just came true. About fractions into this, okay? You can plug those into the quadratic equation and you will get the right answer. But I want to use, I don't want to work harder, I want to work smarter. So what can I do to get rid of these fractions other than beyond just not doing the problem? How did I get rid of fractions earlier? How did I get rid of fractions just a bit ago? Multiply. That's exactly right. What did I multiply by? Multiply both sides by the least common denominator, right? Yep, and you got it, it's 10, right? So the smallest number that all three denominators go into, 2, 5, and 10, they all go into 10. Multiply left and right by 10. What's going to happen? I'm going to do this all in one step. 10 times 3/10 x squared is just, leaves me 3x squared. 10 times 2 is 20. 20 divided by 5 is 4x. And then 10 times 1 is 10 divided by 2 is 5, minus 5. 0 times 10 is 0. Well, now that's much better, right? So I have 3x squared minus 4x minus 5 is equal to 0, and I'm going to use the quadratic formula. Now, when I write the quadratic equation, or the quadratic formula out, you'll usually say the opposite of b instead of negative b. So in this case, b is negative 4, so minus 4 is 4. So that's why you just see me going ahead and writing 4 plus or minus the square root of b squared, 3 squared is 9, minus 4 times a times c, all divided by 2a. And then let's work our way down. 4 plus or minus the square root. 5 times 4 is 20, or negative 5 times 4 is negative 20. Negative 20 times 3 is negative 60. No. Yeah, negative 60. And plus 9, or 9 minus that, how's that going to work out? It's going to look like a mess is what it's going to look like. Okay. Ooh, what did I do? Oh, I made a mistake. Oh, no. I did. Look at what I did wrong. I squared A instead of squaring B. Maybe I shouldn't jump to so many conclusions. All right, let's try, let me get this right. -4 squared, and we write it the right way. So that's going to be 16, and that's going to be minus -60, which is going to be plus 60, divided by 6. And 4 plus or minus the square root of 76 divided by 6. Does 76 break down into prime factors? Yes, it does. Or does it have a perfect square as a factor? It does. How did I find it? Is I just divided by 2 and divided by 2 again, and it worked. So what I found was that 76 is the same thing as 4 times 19. And then cut that off. Square root of 4 is 2. All the terms have a factor of 2 in it. 2 plus or minus root 19 over 6, which becomes 2 plus or minus root 19 over 3. So solutions. Two plus root 19 over 3, 2 minus root 19 all over 3. All right, so we'll call it there. That'll be the day, because it's time, obviously. Any questions? Anybody got anything that's bugging them?